Welcome in, my dear. This vid addresses mesoarchitectures, which is the fundamental structure of simple neural networks, and it also very specifically covers the notation that we're going to use, not just here, but throughout the rest of the videos and the book and the code. So this is an important get start moment. The book that I'm referencing is Statistical Mechanics, Neural Networks, and Artificial Intelligence. It's still in progress, and this particular vid is a prequel for chapters 4, 5, and 6 that address fundamental neural networks. The material that I'm covering here is in support of the class that I'm teaching with Northwestern University's Master of Science in Data Science program, and specifically the course MSDS 458, Artificial Intelligence and Deep Learning. You don't have to be enrolled in that course to get full value, though. I'm putting a lot of material that I'm developing independently of NU onto my own website. Please check out alianajmarin.com. You'll find lots of goodies there. One of the toughest problems that I face when I'm learning something new is that the notation tends to differ from author to author. Sometimes even the same author will change their notation in midstream. That is so maddening. So that's why we're starting early here. Even though our focus later on is on statistical mechanics and the energy-based neural networks, we're going to start with the backpropagation method applied to the multilayer perceptron so we all have a consistent reference point. Before we get started, a little terminology. We're going to refer to microstructure as the material inside a given neural network node. This is usually the transfer function. We'll refer to the mesoarchitecture as a structure of a simple neural network, typically an input layer, middle or hidden layer, and an output layer. And we'll refer to macrostructure as a composite of several mesostructural components. For example, a generative adversarial network is a combination of two different network architectures. The most common mesostructural architecture, at least the one that we usually start with when we begin studying neural networks, is a multilayer perceptron. This consists of typically an input layer, a hidden layer, sometimes called the latent variable layer, and an output layer. This is typically used for classification problems. So running briefly through our notation, the output layer, which we're showing here as O sub 0, O sub 1, O sub 2 for a 3-node output system, is going to have the running index of O up through K. By the way, we're counting these nodes Python style. That means that the first node is always the 0th node. Similarly, we're denoting the hidden layer nodes as H sub 0 up through H sub j. You can see the notation for the 4 different hidden nodes stuck in between the hidden nodes themselves in the output layer. That's H sub 0, H sub 1, H sub 2, and H sub 3. Finally, we denote the input layer nodes as I sub 0 up through I sub I. So just for fun, let's give some values to these input nodes. We're going to create an input vector array with values 1, 0, 1, 0, 1. And you can see that this array is inserted into a Python list structure. Similarly, and again, this is just for fun, I'm making up these numbers as we go along. Let's give some values to the hidden node activations. As we go along, the term outputs or activations will be interchangeable. It's the resultant or what you get out of either a hidden node or an output node. Finally, let's make up some values for our output node activations. In this case, and again, I'm making these up, our outputs are 0, 1, 0. This indicates that that second node, that's O sub 1, because we're counting Python style, is the node that's activated in the output layer, and this is a good result if we're classifying and that second node is actually what we wanted. One little point, this is actually kind of important. Just by way of illustration, I've been using binary values, that is zeros and ones. However, in actual operation, we can have binary values as inputs. We can also have grayscale values, real values, but let's just pretend we're using binary values. Regardless, in our hidden nodes and our output nodes, we're likely to have real valued numbers coming out. So instead of a 0, we'd get, for example, 0.08. Of course, in a neural network, we have connection weights as well as the nodes themselves. When we have a 3-layer neural network, input, hidden, and output, we have 2 sets of connection weights. Typically, we denote these W for the one connecting input to hidden, and V for the ones connecting hidden to output. The subscripts identify the lower layer first and the upper layer second, so the ones connecting hidden to input are going to be the input layer first and the hidden layer second. In this illustration, I'm pointing with those curved pale red arrows to 2 different connection weights. The one connecting the input to the hidden layer is denoted W, that's a small w actually, 4, 3, that's the 5th input node connecting to the 4th hidden node. Similarly, we have V sub 0, 1 as the first, the 0th, hidden node connecting to the second, subscript number 1, output node. In addition to the normal connection weights between nodes in each layer, we also have bias nodes. Bias nodes put scalar values into each of the hidden nodes and the output nodes. They don't operate on the inputs. We'll rarely see these in the architecture, but they're very useful in scaling the outputs of the hidden nodes and the output nodes back and forth across the x-axis and just giving us a more useful output. The indices for the bias nodes are the same as the indices for each layer, so we run from 0 up through j for the bias nodes that contribute to the hidden nodes, and 0 up through k for the bias nodes contributing to the output nodes. Let's briefly touch on the connection between what we've been talking about in terms of notation and what we're going to use in our Python code. Again, this is referring to just very raw Python code, not a scripting language. This is a sort of code that we would use to provide a training wheels example where we can deep dive into how things work. So when we're talking about the nodes themselves within a layer, or the bias nodes, we're talking about vectors. And vectors can be represented, and also arrays can be represented as single elements within a Python list. So what I'm showing here in this second bullet point is that you could have a Python list with some sort of variable first, then the actual array containing, for example, the values for hidden nodes, and then more elements in the list. That last was a little bit of an oops. I said array and I meant vector, but really a vector is a one-dimensional array, so array is the more general term. Now here's a very important little technical coding note. If you're going to code your own neural network using pure raw Python, and we're talking about using vectors and arrays and array multiplication, that sort of thing, you really want to pay attention to this particular little point. The way that the indices show up for a mathematical notation is reversed from that you use in Python array notation. And I've got a whole blog devoted to that topic. Please take a look at it. And if you ever get lost in trying to find things on my blog site, use the categories. There's a list of categories on the right-hand sidebar in the blog. And in this particular case, you want the Python code category, which contains this particular blog. So let's sum up. We've discussed the meso architecture for a simple neural network, specifically the layers, the connection weights between the layers, and the bias weights, which are typically not shown when we give pictures of the architecture. We've talked about how we use Python counting to represent the nodes, and we're representing the nodes for the different layers, and the connection weights, and the bias weights as Python vectors and arrays. We've touched very briefly on how you can represent these Python vectors and arrays as elements within a list that lets us put other terms or features into the list themselves. We'll see examples of that when we start code walkthroughs. And then we've also addressed a real important little technical side note on the difference between mathematical array notation versus Python array notation. We've done plenty to get ourselves started here. In particular, we've gotten through enough notation so that you'll be able to follow along in subsequent videos and also read the code, understand the code. We're just getting started with that, and read the text. So all these things will work together. Should give us a nice, compact learning experience. The next vid in this series is going to address the transfer function. That's really what makes the backpropagation algorithm workable. And then we're going to derive the equations for the backpropagation algorithm themselves. You'll be able to make direct, precise, line-by-line correlations between lines in the code that carry out the backpropagation training algorithm and the derivation results themselves. So we're looking to get that result over these next few vids. Since this is the first vid in the series, I don't have the usual YouTube commercial capabilities set up, but when I do, if you see them available, please do the usual things. For example, like, subscribe, ask to get the notifications, feel free to comment, and to get the written material and access to codes that goes along with this, go over to my blog site if you would, actually to the website alianajmarin.com, find the book tab. There's an opt-in list, and if you opt in, you'll get information about all updates and releases, including code. Thank you for joining me. It's been such a pleasure to have you with me. I'm looking forward to our next gathering. This is Dr. AJ, wishing you a most pleasant day.